Hi everyone. In this video I'm going to cover some complex number questions from the first chapter of AS Further Maths. For these I've tried to avoid questions that also contain Argand diagrams or rely on roots of polynomials too much, as I intend to cover these topics separately, and I'd like to keep it straightforward for people who have only just started A-level Further Maths. In future videos on these topics, knowledge of this will become assumed, as it's pretty fundamental to algebra from here onward, and it's important you get really comfortable with it, even though it's quite a novel concept at first. However, as a general rule of thumb, these three topics are very likely to be combined into one or two questions on AS Further Maths papers. As a result, you might prefer to use Vieta's formulae or modulus argument form in your own solutions to these problems, or even as a Year 13 student, exponential form or de Moriv's theorem. Anyway, let's get started. So our first question is asking us so we've been told Z is 4 divided by 1 plus I, and we need to find Z, Z star, and Z squared all in Cartesian form. So that essentially means A plus BI form. So for Z, which is equal to 4 over 1 plus I, what we're going to do is essentially rationalize this by multiplying by the conjugate over the conjugate, and that will eliminate the i's from the bottom, which is going to give us Cartesian form. So this is 4 times 1 minus I over, and then 1 plus I times 1 minus I gives us 1 minus I squared, and I squared is negative 1. So this is 1 plus 1, which is 4 minus 4i over 2, which is 2 minus 2i, and that's Z. And for Z star, Z star is the complex conjugate of Z. So Z star is going to be 2 plus 2i. And Z squared, just split the page down the middle. Z squared is going to be 2 minus 2i all squared, which is 2 minus 2i times 2 minus 2i, giving us 4 minus 8i, and then plus 2i squared is going to be minus 4, leaving us with simply minus 8i as Z squared. And then what we've been asked to do is to find the quadratic equation of which Z is a root. So we want to use the property here that if we have one root of an equation as being complex, then another root of that equation will be the complex conjugate of that complex number. So Z is a root implies, and this is a symbol meaning that it implies both ways, that Z star is also a root. And if we know that 2 minus 2i and 2 plus 2i are both roots of the quadratic equation, then we can use the idea that Z minus alpha times Z minus beta, where those are the roots of the equation, is the same as Z squared minus alpha plus beta Z plus alpha beta. And again, this is one of the points where you might in general find roots of polynomials, an easier way of doing this, but it's also generally good to know this rule here. So for this one, that will give us Z squared and minus, and then if we sum the two together, then we'll get minus 4Z plus, and then if you multiply the two together, then you will get, so 2 minus 2i times 2 plus 2i is 4. Then the I components will cancel, and we'll be left with an I squared. So minus 2i times 2i gives us 4. So this is our final answer. Next question. Given that 1 plus 2i is one of the roots of a quadratic equation with real coefficients, find this equation in the form z squared plus bz plus c equals 0. So very similar to the one we've just done, where we have 1 plus 2i is a root. So 1 minus 2i is also a root. And therefore, we can use the same idea as before. Z minus alpha times Z minus beta is Z squared minus alpha plus beta Z plus alpha beta. And that will give us, minus alpha plus beta is going to be minus 2, and alpha times beta is 1 plus 2i, 1 minus 2i. And a useful rule to remember, where for z multiplied by the conjugate of z, if z equals a plus bi, then z times the conjugate of z equals a squared plus b squared. And this is another useful rule to remember because it can make calculations a lot quicker. So just to finish the question off, that's going to give us a quadratic equation of z squared minus 2z, and alpha beta, we didn't actually finish, is 1 plus 4, which is 5. So plus 5. And that's our equation. So for our next question, we've been asked to explain whether it's possible for the equation 2x squared plus 2x plus 9 equals 0 to have a real root. Essentially, this isn't really an A-level further maths question. It would appear in normal maths as well, but as a student who maybe just started further maths at the start of year 12, you might not have come across this in normal maths yet, and so I thought it would be a good question to include in the video. I won't go into it in too much detail, but it's to do with the discriminant, which is b squared minus 4ac. And the rule is that if b squared minus 4ac is less than 0, then there are no real roots to the quadratic equation. And so in this case, we simply need to substitute in to b squared minus 4ac. So we have 2 squared minus 4, 2, 9, which is 4 minus 72 minus 68, which is definitely less than 0. And therefore, there are no real roots to the quadratic equation. It's that simple. More of an A-level maths question, really. But there we go. So now to solve the equation z squared minus 2z plus 17 equals 0. So there are multiple ways of doing this, and it's up to you which method you find the most comfortable. You could do this by completing the square or by using the quadratic formula. So I'm just going to complete the square. So z squared minus 2z plus 17 equals 0. Z minus 1 squared minus 1, remember the hidden 1, plus 17 equals 0. So z minus 1 squared equals, so this is 16, so on this side we have minus 16. So z minus 1 is the square root of minus 16, which is plus or minus 4i. And so z is going to be 1 plus or minus 4i. Those are the two roots of the equation. And remember that if z is a root, then z star also is a root. And we can see that here when we have 1 plus 4i and its conjugate 1 minus 4i, both being roots of the quadratic equation. So I just realised that for the last 10 minutes I was not actually screen recording, so I'm just going to go over these problems for a second time now. Rookie mistake. So we have a cubic equation here. F of z equals z cubed plus 3z squared plus kz plus 48. And we've been told that 4i is a root and we need to solve completely the cubic equation. So for this we are going to use the idea that, again, if 4i is a root, then minus 4i is also a root. But before we get onto any factorizing or anything like that, we just need to find out what k is. And for that, we're going to use the idea that if z is a root of fz, then fz equals 0. So we need to substitute 4i into the equation. Set it equal to 0 and then solve this for k, which should be a real number, by the way. So this is going to give us minus 64i. Remember, I cubed is minus I. And 4i squared is going to be minus 16. So here we have minus 48 plus 4ki plus 48 equals 0. So to tidy that up a little bit, we have minus 64i equals minus 4ki. So 64i equals 4ki and k equals 16. And now that we've found the value of k, this next part of this problem is to completely solve the cubic equation. So in order to do that, I'll just split the page here. So we need to find a quadratic which has the roots 4i and minus 4i. And then when we have that quadratic, we can divide our original cubic equation by that quadratic in order to get the final linear factor and extra third root, which should be real because we have two complex roots and therefore the last root must be real because they come in conjugate pairs. So for 4i and minus 4i, same idea as before, the quadratic is going to be z squared plus 16. And this is a factor of f of z, and therefore we can use polynomial division to finish this off and identify the last factor. So we have 3z squared plus 16 plus 48. And we're dividing that by z squared plus 16. So to do that, we'll have z cubed plus 16 plus 16z, subtract, we get 3z squared plus 48 plus 3z squared plus 48. We get a remainder of 0, which is what we want, and we have this as the quotient, So that therefore will tell us that z plus 3 is a factor, and therefore by the factor theorem we know that minus 3 is a root. So our roots to the equation were 4i, minus 4i, and minus 3. Moving on to the next one, as if a cubic wasn't enough, we now have a quartic. And it's f of z equals z to the 4 minus 12z cubed plus 31z squared plus 108z minus 360. And we've been told that 3 and minus 3 are roots of the equation, and we need to find all the solutions to the above. So that's going to be 2 more roots. And they're either both going to be real or both going to be complex, because, and I bet you can guess which given the title of the video. But because complex roots always come in pairs, we know that the other 2 roots must either be 2 real roots or 2 complex roots, because they've already given us 2 real roots. So what we need to start by doing is identifying the quadratic which has 3 and minus 3 as its roots. And that's going to be z squared minus 9 is a factor. So we need to divide f of z by z squared minus 9, and then we will get another quadratic which we can then factorize, and or not factorize because it's likely to have complex roots, but we can solve it to find those complex roots. So we z to the 4 minus 12z cubed plus 31z squared plus 108z minus 360, and we're dividing by z squared minus 9. So polynomial division, it can be a little awkward at first, but it's a skill that you very much build up through A-level maths as well as further maths. So by the end of the course, you should be quite comfortable with this skill. So we have z squared this is going to give us 40 z squared plus 108 z, and then we'll have minus 12 z minus 360, and then we're going to have plus 40, and that will give us our remainder of 0, which we were looking for. And so we have z squared minus 12z plus 40 is a factor, and we just need to find the solutions to this equation, and those will give us our other 2 roots. So I'll use my favourite method of completing the square for this one, but remember you can use the quadratic formula. You can probably even use your calculator to do this. Some calculators can anyway. So we'll have z minus 6 squared minus 36 plus 40 equals 0. So z minus 6 squared, and we're going to have a minus 4 on the other side. So z minus 6 equals the square root of minus 4, which is plus or minus 2i. And so z is going to be 6 plus or minus 2i. So these are the other roots of the equation, along with the original roots of 3 and minus 3. And that's it for this video on complex numbers. I hope that helped, and thanks for watching. See you next one on Argand diagrams.